You've probably heard of the double-slit experiment, right? For centuries, it's been the cornerstone of quantum physics, a mind-bending demonstration of how light and even particles can act like waves. But what if that understanding is incomplete? A new theory is shaking up everything we thought we knew about light, interference, and the very nature of quantum reality. Today, you'll discover the revolutionary idea of dark photons. The double-slit experiment has always been a fascinating mystery. Shine light through two narrow slits and boom. A pattern of interference appears, as if the light somehow passes through both slits at once. Even sending one photon at a time creates that same wave-like pattern. How? For decades, the answer was simple. They behave like waves until we measure them. But now, a bold proposal from physicists at the Max Planck Institute, in collaboration with ETH Zurich and Brazil's Federal University of São Carlos, suggests something even more radical. Maybe waves aren't needed at all. They've introduced a new model called the dark photon interpretation. According to this theory, the interference pattern doesn't come from overlapping waves, but from interactions between two quantum states of light. Bright photons, which we can detect, and dark photons, which exist but remain hidden from our instruments. When a photon encounters the slits, it doesn't split spatially like a classical wave. Instead, it enters a superposition of visible and invisible states. What we see is actually the result of a kind of quantum conversation between the detectable and the undetectable. In traditional quantum theory, measuring which slit a photon goes through collapses its wave function, destroying the interference. But in this new view, it's not about destroying anything. It's about shifting the photon's state from visible to invisible. Measurement doesn't alter the path. It alters the coupling with the environment. This idea ties into experiments like the quantum eraser, which show that how we choose to measure changes what we see, even after the fact. Under the dark photon model, the pattern was always there. What changes is whether we make it visible. Those dark regions on the screen where we see no light. They might not be empty at all. They could be filled with dark photon states, invisible but real, like hidden rooms in a house we thought we knew. Maybe we've just never had the right kind of flashlight. The implications are massive. If these hidden states exist, then future quantum sensors and detectors could tap into them. They might unlock ultra-secure communication, more powerful quantum computers, and entirely new ways to process information, using what was once thought to be nothing. And this isn't science fiction. Other real-world experiments support it. Weak measurements show we can extract data without fully collapsing a quantum system. Entanglement experiments suggest particles influence one another instantly, across space. Even gravitational wave detectors like LIGO use quantum light tricks to catch faint ripples in space-time. And understanding hidden photon modes could push those tools even further. Interestingly, dark photons already show up in cosmology. Some scientists believe they could even make up part of dark matter, unseen, undetectable, but shaping the universe. This model could be a bridge between quantum optics and cosmology, a unifying step towards something bigger. So where does that leave us? Not with a final answer, but with a better question. What else is out there that we simply done to know how to detect yet? Thanks for joining us in this deep dive into the dark photon theory, a bold reimagining of light and measurement that could change everything we thought we knew about the quantum world. Until next time, keep your mind sharp, your curiosity alive, and your photons bright or dark.